Okay, so welcome again. So for the last talk of today, we have Edson Sampaio from the Universidade Federal do Ceará in Fortaleza, who's speaking about an overview of the metric geometric version of Zariski's multiplicity congestion.
Okay, thank you, Fernando. Thank you also for the invitation to participate in this event. So sorry also for I'm not in person. Maybe next time. So let me start saying some introduction and motivation. But in fact, before, let me say some initial considerations. The results present here were proved by many people. Example, Bribraí, Conte, Efraim, Fernandes, Bobadilla, Gal, Hironaka, Lippmann, Milman, Fan, Risley, Tessier, Verbitsky, Zariski, etc. And myself as well. So many of them were not proved by myself. But if you can find, if you want to find the results by myself, you can find it in my ResearchGate webpage and also in my Rome page. Okay. So the main motivation of this talk is the well-known Zariski multiplicity conjecture, which says that the multiplicity of hypersurfaces are topological embedded invariant. In fact, in order to be more precise, if you have two functions, analytic functions from Cn to C, let me say reduce it here, and if there is a homeomorphism from Cn to Cn sending the origin at the origin, and send the zeros of f to the zeros of G, then the multiplicity of f is equal to the multiplicity of G. In this case, multiplicity means the order of f, because I'm taking reduced analytic functions. Okay, I think I will define multiplicity in a more general setting. Some in the next slides. Okay? But since there are so many people that work in that problem, I decided to do an overview only in a special case of this conjecture, that the geometric version of this conjecture. In fact, I'm interested in the geometric nature of the multiplicity. So I speak about some important results in that direction. Okay. But the first important result that gave a partial answer to the Zariski multiplicity conjecture was the Efraim-Trotman theorem. It gave a positive answer when the homeomorphism is a C1 diffeomorphism. In fact, because this result, we have a more general result like that, but in codimension, here is codimension 1, is only one analytic function here. But in n codimension, we have also a result like that, and it was proved by Gao and Lippmann in 81. Okay, they prove it if you have two complex analytic sets, X and Y, and you have a homeomorphism from Cn to Cn, sending X to Y. Here, everything are germs. Okay? At least I say in a different way. Okay, so if you have a sub function phi, such that phi is phi and its inverse have derivative at 0, so the multiplicities are equal. I will give an idea how to prove that. In fact, I some years ago I gave a different proof of that result, and in a short way, I will give the idea how to obtain that short proof of this result. So, because that, if we try to generalize, for example, if you think phi is a C1 diffeomorphism, so the derivative is bounded, so in particular is by Lipschitz, for example. So the natural question is ask if the multiplicity is by Lipschitz invariant. That is what say the following conjecture. Here we call it metric version of the Zariski multiplicity conjecture. If you have two sets, X and Y, with the same dimension, if their germs at 0 are by Lipschitz homomorphic, and by Lipschitz means here there exists constants C and C prime, such that 1 over C prime X minus Y is less than A minus Y, less than C times X minus Y. Of course, if you have a map from X to Y, of course, satisfying that condition. Here we call C prime and C the Lipschitz constants of phi. Okay? So the conjecture says that if you have a homomorphism between two guys like that, then the multiplicity of them are equal. And in fact, we have also a global version of this conjecture when we consider, instead of analytic set, we consider algebraic sets, and instead of by Lipschitz homomorphism around the origin, we consider by Lipschitz homomorphism outside of compact sets. That means by Lipschitz homomorphism at infinity. Okay? So if you have something like that, so the conjecture is the degree of X is equal to the degree of Y. So the first theorem, the first result that I want to say about those conjectures is not the first one, but it's important to understand everything after. So the first says that these two metric versions of the Zariski multiplicity conjecture are equivalent. That means if one is true, the other one is true, and reciprocally. Okay. This was proved by Bobadilla, Fernandez, and myself in 2018. And in fact, the first important result on that conjectures was proved by, in fact, was proved when in fact they hold, now I can say they hold true, because if one is true, the other one is true. So they hold true when D is equal to 1. That means for curves, the conjecture is true. So I can say only the conjecture instead of the conjectures. Okay. So this was proved in many works by Frank Tessier and in 1969, Fernandez in 2003, and Neumann Pichon in 2014. And oops, I did something wrong. No, yeah. In fact, they also hold true for Rugo's equivalence on functions in codimension 1. This was proved by Riesler and Trotman in 97. just to know the definition. Now you are in codimension 1, so x is the zeros of some function f, y is the zeros of some function v. So we have a bijection from Cn to Cn satisfying more or less the Lipschitz condition, but here is for any x close enough to 0 in Cn and ny close enough in the zeros of f close enough also to 0, and also for the inverse. If you satisfy these two conditions, we say is Rugose. Okay? And if you also satisfy the contact condition, if you can control f and g by constant when you compose with the homomorphism. If you have a homomorphism that satisfies these two conditions, they prove the multiplicity of f is equal to the multiplicity of y. And this was, you can see when I'm present the slides, you can see the reference just in the bottom of the slide, okay?
Yes.
So another important answer to the conjecture was proved by Comte. He proved that the conjecture, the version of the Zariski multiplicity conjecture holds when the involved Lipschitz constants are close enough to 1. In fact, he proved that if the constant, like as I said, C prime and C satisfy something like that, let me call D the complex dimension of the sets. I call D. So this is less than 1 plus 1 over m, where m is the maximum of the multiplicity of x and the multiplicity of 1. If you have a homomorphism that satisfies that condition, by Lipschitz homomorphism that satisfies that condition, he could prove that the conjecture holds. Okay? So this was proved in 98, and has a consequence of that. Of course, if you have a family of analytic sets xt and a family of bi-Lipschitz homomorphism phi from xt to x0 with constants ct and ct prime satisfying that, of course, if satisfy that, of course, for t small enough, will satisfy that because m is bigger than 1, of course. So up to some moment, this will be less than this. So, with in fact, he could prove this result in family. In fact, this implies, for example, if you have a strong Lipschitz trivial family, that family is ecumultiple. That means that the multiplicity is equal for any element of the family. But this is also a consequence of a result of Hironaka. Hironaka, in fact, proved that if you have a B regular family, that family is ecumultiple. So, but
Edson, can you hear me? Because it was a cut.
I saw now. When the
no, you were no,
when the connection
just a half a minute ago.
I had said about I have I was talking about this item is a consequence of Hironaka. Did you hear me?
Yeah, you already said.
Yeah, okay. So
you can continue there, yeah.
Okay. So let me continue. Another result about that now was a generalization of the result of Riesler and Trotman, now proved by Kohn, Milman, and Trotman in 2002. They proved more or less in the, now for in codimension one also, but instead of Rougaud's assumption, they only ask, because in particular, Rougaud's assumption implies the homeomorphism is a bi-Lipschitz homeomorphism between the zero sets. But they only ask the homeomorphism satisfy the same bi-Lipschitz condition. That means if you only, they only ask something like that. Something, this is when phi, of course, when phi of 0 is 0. So this kind of map is called semi-bi-Lipschitz map at 0, for example. So instead of Rougaud's, they ask this condition and, of course, the contact condition, that control between the functions. The second condition, let me show just here. Of course, instead one semi-bi-Lipschitz condition, and of course they have also the second condition. If you have these two conditions, they could prove also the Zariski multiplicity conjecture. And also the conjecture holds for normal surfaces. This was proved by Neumann and Pichon in 2012. And the conjecture holds for the case when one of the multiplicities is equal to 1. That means if one is, if you have a bi-Lipschitz homomorphism between x and y, and one of them has multiplicity equal to 1, so the other one has multiplicity equal to 1. Then this was proved by Bibraí, Fernandes, Ledon-Tang, and myself with an extra condition that the homomorphism by Lipschitz have to be also semi-algebraic. And then in the same year, I proved this the theorem without that semi-algebraic condition. This here, these papers. Okay, and then also in 2016, these two results was proved in 2016, and also in 2016 another paper, the third paper, Fernandes and I proved the conjecture is true when we have, you are in the hypersurface case and the dimension is 2 for surface, that means, right? That for surface in C3, and of course we ask more. We ask surface in C3 by Lipschitz equivalence, now not only in the sets, only in the surfaces, but also the homomorphism is by Lipschitz is defined in the ambient space from C3 to C3. Okay, if you have that, so the multiplicity. And then I proved a generalization of that result. Was published in 2020. I proved also in the hypersurface case and also in the ambient by Lipschitz case. I mean, when you consider by Lipschitz homomorphism defining the ambient space. Okay, so if I assume that each irreducible component of the tangent cone has singular set with dimension at most 1. of course, if you are in the case of surfaces, the tangent cone is a surface as well. So the singular set of each reducible component is at most one, of course, because the singular set has dimension at most the dimension minus one, right? So I could prove that, and also recently we proved that the conjecture holds true if the dimension is 2. Now I don't care about co-dimension or if the ambience or if the homomorphism is defined or not in the ambience. If you have two surfaces and the bidirectional is between these two surfaces, so the multiplicity are equal. This was proved by Bobadilla, Fernandes, and myself in 2018. And unfortunately, we proved that the result of the conjecture is not true when the dimension is greater than 2. In fact, we presented a counterexample that this was our work joint with Bibraí, Fernandes, and Verbitsky, proved in 2020. So I will give some hints, some ideas, some sketch of idea, some sketch of the proof of these two last results. Okay, and also I want to talk about the real counterpart of this problem. This, of course, if you consider just the real version of the Zariski conjecture, we have that conjecture is not true, because if you take the real cusp and the line, the real line, you can obtain a homomorphism from R2 to R2, sending the cusp to the line, and they have different multiplicities. But if you consider by Lipschitz homomorphism, I don't know, but there were conjecture about that said that if you have two germs at the origin of irreducible real analytic sets, and if you have by Lipschitz map from Rn to Rn with subanalytic and arc-analytic that send x to y, then the multiplicity of x is equal to multiplicity of y mod 2. Of course, more important here. You can find counterexample without mod 2 if you remove mod. So let me say, so many people also work in that problem. Let me say some of them. Firstly, I think the first result on that was proved by Risley in 2001. He proved that conjecture is true for n equal to 2. And so this was proved by for n equal to 2, but even with the equality without mod 2, in this case for n equal to 2, we can have, in fact, the conjecture without mod 2. But this is the only case, the dimension equal to 1 is the only case that holds. This was proved by Fukui, Kurik, and Paunescu. And in fact, this well, the conjecture was posed in that paper as well. And so this was proved in the hypersurface case in codimension 1 by Valette in 2010. And also it was proved like a region of the Gauss-Lippmann theorem by myself in 2021. That means if you have a homomorphism from Rn sent next to y, such that the homomorphism and its inverse has derivative at 0. So, and last year as well, it was proved in general by Fernandez, Yellowneck, and myself. So if the time allows me, I will give some hints of that. So I will start to say some preliminaries about that. Okay, so let me start. Say some preliminary. Let me remind the notion of tangent cone. If you take a set X in Rn and a point P in X, we say that V is a tangent vector of X at P if there exists a sequence of positive numbers Tj and a sequence of points xj in X such that the limit of Tj is 0 and this limit is V. And we denote all the tangent vectors of X at P by this guy, by this way, and we call it the tangent cone of X at P. So another important tool here is the strict transform of a subset X under the spherical growing up beta n that send X R to R times X, like that. And we denote the strict transform by X prime, the inverse image of X minus 0, the closure of that, and the boundary, boundary X prime, just to be the intersection of X prime with Sn times 0. So we can, it's exercise to see that when you consider the link of the tangent cone, the intersection with the sphere, times 0 is just the boundary. Is another way to see the tangent cone of a set. So I will say that a point in the boundary is a simple point of the boundary if there is an open set U with X in U such that when we intersect the strict transform X prime with U and remove the boundary, this gives a finite number of connect components, and each one of them is a topological manifold with the same dimension of X. And when put the boundary, which one, in fact, the Xi union of the boundary inside of U is a topological manifold with boundary. It's something like a book, and the part that glue the sheets of the book is the part which is in the boundary, and the Xi's are the sheets of the book, something like that. And we collected all the simple points in this way, SMP of the boundary. We can prove, for example, this guy is an open dense subset of the D-1 dimensional part of the boundary. Of course, if there is, if it's not in. So we can define a functional that sends a point in the simple set to the number of connect components of this germ. Just the number. This will be just the number of connect components xi. Like in this case, the k of x will be r. Okay, and then of course it's not hard to see this definition is locally constant, and then it's constant in each connect component of the simple part, and we denote that constant by kx of Cj. Cj is a connect component of the simple part. Okay? And in the case when X is a complex analytic set, we can show that there is some analytic set with dimension less than the dimension of X, such that when you take a reducible component of X J, this guy, when we remove the set, intersect only one component of CI. Of course, I'm identifying the tangent point with the tangent point times 0, of course. And now we define this since this intersect only one, so it makes sense to define this guy, kx of xj, be just the kx of ci, that ci that this guy intersects. So I think I'm fast now, but let me try to give an interpretation, a quick interpretation of that. If, for example, if you are in the case x is 0 of a function f, and you write f like that, fm in homogeneous, you take a homogeneous decomposition, fm plus 1, such. Of course, when fm is different to 0, and then now we decompose fm in irreducible components like that, 8-1, k1, such, 8r, kr. So what I'm saying that xj is the 0 of some 8j, and the kx of xj, so xj is the tangent point, okay, is that kj. You can prove that. I don't have time to that, but it's an interesting exercise to prove that. So it's a good interpretation if you keep in mind, okay? Okay, so in particular, of course, we obtain an important formula for that. Since I'm in the reduced case here, I did not say, but assume that f is reduced. So the multiplicity of the zeros of f, which is equal to the order of f, is equal to the sum of the k x of xj times the multiplicity of xj at 0. You can prove that. In this case, it's easy because m is the multiplicity here, m, and of course m is equal to the sum of the order of hi times ki, for example. I goes from 1 to r. Okay. And I used to say that homomorphism from x to y is a noispheric homomorphism if that composition, which is a homomorphism because outside of 0 and of the boundary, beta m is a homomorphism, in fact, a differomorphism. So this is a homomorphism always, but I will say that this is a noispheric homomorphism, and this extends to a homomorphism from x prime to y prime. And in this case, we denote the part in the sphere by V8. When this is a this is a prime. A prime, when we are in the boundary, we denote the spherical part by V8. This is important. So with that, I'm going to generalize the notion of derivative. So I will say that a homomorphism 8 from x to y is a Bloch-spherical differentiable at 0 if there exists linear isomorphism, okay, phi from Rn to Rn, such that V8 is that ratio, okay, here over the normal phi. Of course, an important example of that is, of course, when phi is a homomorphism such that phi and phi, its inverse has derivative. So we can prove that the restriction of phi to x is a Bloch spherical differentiable at 0, has the above definition, and the V8 is just the derivative of phi over the derivative, the normal. And of course, if you have that, I can prove, for example, this. If I can prove this theorem, I prove the generalization of Gauss-Liebner because the theorem is, if there is a Bloch spherical homomorphism which is Bloch spherical differentiable at 0, so the multiplicities are equal. But as I remarked in the example, the assumption on the Gauss-Liebner theorem implies this assumption. So of course this is more general. So just to define the multiplicity, I have some time yet. Sorry. Let X be an analytic set in Cn with pure dimension K, okay, and take a orthogonal projection. Sorry. P from Cn to Ck, such that the kernel of the projection intersect with the tangent cone is 0. So in this case, we can prove that we can find a small neighborhood U of the origin of the origin of Ck, in fact, so Cn, okay, such that this cardinality, when T is outside of some analytic set sigma of dimension less than K, okay, this number does not depend of T, and also this number does not depend of P or when satisfy this condition. And this is what I call the multiplicity. Of course, this coincides with the order of a function, of a reduced function, in the case of hypersurfaces. Okay, so this is the definition of multiplicity. I like that multiplicity. I'm a geometer. I'm not an algebraist, so I prefer that one. So the theorem is that. Let me give a hint of how to prove that. But let me remind K results. I don't have time to prove that. But if you have a Bloch spherical homomorphism, so of course it's not hard to prove that the number of reducible, the connect components are preserved because it's a homomorphism. Because if you have a Bloch spherical homomorphism, we have a homomorphism from x prime to y prime that send the boundary to the boundary, so send the complement of the on the complement. So it's not hard to prove that. And the second is that formula that I already said, okay. So it's get the by assumption there is some R linear isomorphism phi from Rn. It's not no, from R to N. I'm in Cn, okay. I'm identifying Cn with R to N, so that V8 satisfy that, and also because that remark the boundary is just the Cx times 0. We prove phi is a homomorphism between the tangent cone to the tangent cone. In particular, it sends bijectively reducible components of the tangent cone of x to the reducible components of the tangent cone of y. So let me call x such x prime, x r, and y such y prime r, the irreducible components of x and y respectively. such that we have that, because this is the last condition. And so you take the complexification, since this is a real analytic map, this is a complex analytic map that sends the complexification of xj to the complexification of yj. And we know it's not hard to prove in this case. The multiplicity is invariant by complex diffeomorphism, which is the case. And also this was proved by Ephraim. When you are in the reducible case, the complexification is isomorph to the set times the conjugation of the set. Of course, this has the conjugation has the same multiplicity of x. So this guy has the multiplicity of x squared. So we obtain like that. The multiplicity of xj square is the multiplicity of this guy. So we obtain that the multiplicity of xj is the multiplicity of xi. Since we have that these numbers are invariant also by the first proposition, the k results, we obtain the sum of the left side is equal to the sum of the right side, but the sum of left side is the multiplicity of x, and the right side is the multiplicity of y. So we prove this is more like that. In fact, I have a lot of things to do, but this is the idea more or less how to prove that. As a consequence, you obtain Gauss-Liebman theorem. If you take these examples, these two kind of cusps, in fact, you can find a Bloch-spherical homomorphism from x to y, just composing, you take the Piaget parameterization of that and the Piaget parameterization of that also, and compose with inverse of one, and you can prove, in this case, that composition is a Bloch-spherical homomorphism, and the V8 is the identity. So this is Bloch-spherical differentiable at 0. However, there is no homomorphism from C2 to C2 sending x to y because they have different Piaget pairs. So in particular, our theorem is more general than this. Okay, let me talk about the answer to the method Zariski multiplicity conjecture. Let me hint how to prove the invariance of our surfaces. In fact, we prove that it is enough to prove when x and y are irreducible homogeneous algebraic surfaces. In fact, this was how we proved that the global version is equivalent to the local version, because we proved that the global version is equivalent to prove the global version for homogeneous sets, and also we proved for local, in the local case, we proved that for solve the local case is enough to solve for homogeneous sets. But in the case of homogeneous sets, the multiplicity and the degree are equal. So this is why they are equivalent. So there is a step here, and the step is use two important results. When you have a bidirectional homomorphism between two sets, we have a bidirectional homomorphism between the tangent points, proved by myself, and also a bidirectional preserves that function kx. So we use that formula to arrive in this this climb here. And so using spectral sequence, we could prove, for example, when we are in the irreducible case for homogeneous algebraic surfaces with degree d, the torsion of the second homological group is just z over dz. Since we have a homomorphism, if you have a bidirectional homomorphism from the sets, you have a bidirectional homomorphism the tangent cone, so you have a bidirectional homomorphism between the homogeneous, irreducible homogeneous sets. So we have in particular a homomorphism. So in particular, the Taugean are isomorphous. So of course, in this case, we have the same multiplicity because the multiplicity and the degree are equal, as I said. So this is more or less how to prove. I have not so much time. Let me give an idea how to prove, to find a counterexample of that conjecture. So the idea is the following: we take two distinct odd prime numbers and let A be an embedding or in B degree 2P of the projective line times the projective line in some CPN. They, of course, we take B to be the same, but with B degree 2Q. Okay. And because the way we embed, we have in fact, A has degree 4P and B has degree 4Q. And then in particular, the degree are different because we took different primes. Let X and Y be the affine cones of A and B, respectively. And so X and Y are homogeneous algebraic sets. Since A and B has dimension, complex dimension 2, X and Y has complex dimension 3, for example. So we take L to be the intersection of X with the sphere, X with this unity sphere, and M, sorry, this is Y, okay? This is Y. Okay, so M is the intersection of Y with the sphere. So here we, since this is smooth, for example, X is a complex analytic set, complex algebraic set with isolated singularity. So M and N are smooth in this case. In fact, we can prove that they are simply connected, compact oriented, and of course 5-manifold because X and Y are of that complex dimension 3, as I said. So the intersection has real dimension 5. And with that, we can use the Ismail-Baden classification to prove that L and M are diffeomorph to S2 times S3, S3 times S2. I don't care about that. So in particular, because they are both of them are diffeomorph to the same guy, they are diffeomorph. So if they are diffeomorph, since they are diffeomorph and they are compact, the derivative is bounded. So in fact, they are by Lipschitz homeomorph. But if you now it's task. If you have a Lipschitz homomorphism between two sets, you can obtain a Lipschitz homomorphism between the cone, the real cone of these two sets. And when you take all the line, the real cone is take all the half lines that pass through the set. But when you take that, you come back to X and Y. And so we obtain that the X and Y are Lipschitz homomorph. And then, but the multiplicity of X is equal to the degree of A, and the multiplicity of Y is equal to the multiplicity of B. Sorry, the degree of B. So they have different multiplicities. So we could find a counterexample. Okay. I think I don't have time to say more. I will stop here. Thank you very much for your attention.
Okay, thank you, Edson. Okay, thank you. So, any question or comments?
Maybe I have a comment. Hi, Edson. Maybe I have a comment concerning the question of Zariski in family, in new constant family. There is some new results and yeah, can maybe mention.
There is a very recently result. Who asked that? I could not see.
That's me, Georges Comte.
George.
Hi, George.
Hi.
Yes, this was, there is a very recent result posted on archive by Fernando Bobadilla and I think Pelska, which answered the Zariski multiplicity conjecture in the case of families. That means if you now take in fact, these two problems are equivalent, but what they proved was the following. If you take, for example, a function, analytic function from Cn times C, of course, like something like that, has a germ, okay, sending C times 0, so that when you look like ft to be f fixed t, this is an analytic function with isolated singularity. So there is a number, a Milnor number defined. I'm assuming that this has isolated singularity, so we have a Milnor number associated to that. So the conjecture, this was also now by Tessier conjecture. When this is constant, this implies the multiplicity of the zeros of ft is constant. Say it's the same of the f0, for example, or t is more enough. So the answer just like that. So the answer is just this question, but there is a well-known result by Le Duntrang and Ramanujan, which say that for n different to 3, this condition implies that we can find a family of homomorphism Phi from 0 to Cn that sends the 0 of ft to the zeros of f0, for example. Just in this case, it's just we are in the Zariski multiplicity conjecture, but the family in the family case. But we have a homomorphism sending the zeros of a function f to the zeros of function f0. So they just to finish, they prove that if you have a family like that of homomorphisms with and the family is isolated singularities, have isolated singularities, so the multiplicity is constant. Using spectral sequences, in fact, they could refine a very nice idea from Mark McLean, and they could control a hard part of the Milnor fibration when you consider the flow of homology, and then they could prove that.
Okay, thank you, George.
Yeah, I just want to say, I think since I did not finish, I had some important remarks, which is, of course, the Zariski multiplicity conjecture is still open, and but even in Zariski multiplicity conjecture, the method version is still open in codimension 1. And of course, in fact, it's still open in codimension 2 because our counterexample lives in codimension 3. So the method version of the in codimension 1 is open, and of course, Zariski multiplicity is open, but in family is not open anymore because the theorem of Bobadilla, Fernando Bobadilla and Pelska.
Okay, thank you. One more comment? Yeah. So if not, we thank the speaker again.
Thank you.
Okay, so we'll resume tomorrow at 9. Remember that we have a reception at 4:30 p.m. Thank you. Molto bene.
Ciao Fernando.